and you whack that light through a spectrum, then that light gets broken up into its component parts. It's a bit like a cocktail being brought to you in a bar, and then by, I suppose, looking at the cocktail menu, you can see exactly what's inside those cocktails. Anyway, each element in the periodic table, when it's giving out light because it's hot, for example, it has a unique set of lines when that light is split up, and from that you can work out what elements are present. We've done loads of examples of those. So how else can we explore space? Crewless spaceships. There are two kind of technologies to do with crewless spaceships that you need to be aware of. One is gravitational assists, so this is sometimes called a slingshot maneuver. So here's a planet. The planet is going round in its orbit around the sun with at some orbital speed. Because it's got orbital speed, it's got kinetic energy. Your little spacecraft allows itself to be captured by the planet, and then it's swung round by the planet because it's in orbit, and not only has it got its own kinetic energy from having been moving before it's got into the planet, but now it's also got the kinetic energy of from being associated with the planet as the planet's going around its orbit as well. So you add the two speeds together. So that's a gravitational assist. It's a way of getting a boost of speed without having to burn fuel. Okay, ion drives. If instead of throwing out the back lots and lots of exhaust gases which use up fuel very, very quickly, even though they give you a decent amount of thrust, if instead of that you use an electric field to accelerate tiny charged particles, then that tank, if you like, of fuel of charged particles lasts far longer because it's a much more energy efficient process. You can only use it when you're far or reasonably far away from planets because it does provide tiny thrust, so you'd never be able to leave the planet's surface with an ion drive, but it's a much more efficient way of moving around when you're far enough away from the gravity of planets. Crewless spaceships, some of them can end up just orbiting the moon or whatever it's the moon of whatever planet you're talking about, at which point they are known as satellites. But this applies to satellites in orbit around Earth as well. The higher up the satellite is, the slower it orbits because the weaker the gravity field strength is from that planet, so it can orbit slower. A geostationary satellite in orbit around Earth orbits so slowly because it's so high up that the geostationary satellite orbits Earth at the same rate that the planet itself turns, so it stays above the same position on Earth, so it can be used for like Sky TV, and this is why the satellite dishes point at the same place in the sky, because they're pointing at a geostationary satellite. The orbital period is the time for one orbit. Do you remember that word period? It's all about number one, so it's the time for one Earth orbit. Crewed spaceships, this is the sexy thing. What are some danger points? Danger points are launch, because of all this vast quantity of high explosive rocket fuel, and the ignition must be down to microsecond exact perfection, otherwise the whole thing can blow up, killing everybody on board. Re-entry is potentially very dangerous because it's a huge amount of kinetic energy being converted to heat energy. There's radiation up in space. There's obviously no atmosphere to absorb the cosmic rays, so you get a much higher radiation dose in space, which could lead to cancers in long-distance space travelers. And evacuation. It takes several hours at the absolute quickest to evacuate from the International Space Station if there's a medical emergency. Now, if you're at Mars, it would take like 6 months at the very quickest to evacuate from Mars if there was a major medical incident or whatever. So that's a big risk. What are some benefits of specifically human space flight? Well, think about robotic surgery. So spacewalks are very dangerous, so we try and minimize spacewalks on like the International Space Station when we can, and to minimize them we've used robots with now very, very, very dexterous hands in inverted commas, and so now robotic surgery does a lot of very, very delicate, very small scale surgery, keyhole surgery in hospitals. It's something, and remote robotic surgery is something Dundee has pioneered. So a doctor on one continent can use a robot in another continent to be doing an operation, even though the doctor doing the operation or controlling the robot is thousands of miles away. Also, crewed spaceships, very useful for studying how the body is going to respond to long periods of time in space. So there we go. W equals mg, the weight force on an object on different planets. The weight force measured in newtons is mass of the object in kilograms, and little g, the gravity field strength you can find on the datasheet. Here's the triangle. Fundamentally, mass doesn't change. Mass is like the number of atoms in something. Mass is measured in kilograms. It's not going to change. However, the gravity field strength of the planet you're on does change if you go to a different planet, and so the weight is going to change. Even if you stay associated with the planet you're on, as you go higher and higher and higher and higher up, the gravity field strength gets smaller and smaller and smaller. So very, very, very high up, then the weight force on the object is going to be a little bit less. Anyway, most of the case in Nat 5, it's something goes to a different planet. Does the mass change? No. Does the weight change? Yes, because the gravity field strength is different. Right, onto the nuclear topic. What the hell is the point in learning about nuclear stuff? It's in manufacturing processes like filling tubes of toothpaste and creams and that good stuff, and manufacturing paper, silicon chips, sterilizing stuff like any plastic medical instruments like syringes, which give people vaccinations, because you can't put plastic or medical things in autoclaves, which are like pressure cookers, because they'll just melt. Things like makeup gets blasted with radiation before it's sold, so that there aren't any bugs on it. So there's lots of uses of radiation. Smoke detectors have radiation in, and yeah, so lots of good uses for them. Medical scans, cancer treatments, power stations, nuclear processes, how stars burn. It's how we age, old stuff. So if you've ever wondered when some old stuff has been dug out of the ground, how the hell do they know with such precision how old it is? Well, it's because of radioactive dating, and of course species-ending nuclear bombs are a use of nuclear processes. Nuclear decay is when a radioactive particle spits out bits of radiation. There's alpha bits, gamma bits, and gamma bits. Okay. The level of ionization, you need to know what ionization means. Ionization is when radiation rips off electrons from an atom, and if a bit of radiation rips off electrons, that's called ionization, and that kind of stops the radiation from going any further. So if a radiation is very ionizing, then it doesn't penetrate very deep. So alpha, now what decides the amount of ionization is the electric charge on it. So alpha is very ionizing because it's got a charge of positive 2, so it interacts a lot with the surface atoms on things it hits, so it doesn't get very deep. Beta is a bit less ionizing because it's only got a size 1 charge, because it's an electron, so it interacts a bit but not a huge amount, so it gets deeper in. And gamma light is a form of light. Light doesn't carry any electric charge, and so it doesn't interact with the surface atoms, and so it gets deeper. And where a radiation stops is where its energy gets dumped. So the absorbed dose, if you're hit with some radiation, is energy divided by mass. The absorbed dose is measured in grays, and here's the formula. Now, if the cells you want to kill are very resilient, they'll need a big dose to kill them. And so if you're wanting to give some cells you want to kill, I don't know, maybe they're cancerous cells, a big dose, you need to give them a big amount of energy. So how do you get a big amount of energy? Well, you want some radioactive material which is going to be spitting out a lot of radiation. And so something spitting out a lot of radiation, we say that thing is very radioactive, or it has a high activity, because radioactivity or activity is the number of bits of radiation spat out divided by time. Spitting out a bit of radiation is also called a decay. So activity is also the number of decays divided by time. So activity is measured in becquerels, BQs, and there's the formula there. Sorry, there's the triangle there if you want it. And the higher the activity number in becquerels, the higher the number of becquerels, the greater the number of radioactive bits spat out, and the greater the number of radioactive particles spat out in a certain amount of time, the more energy which comes out. Okay, so that's activity. When you're irradiating stuff, which means when you're deliberately having radiation hit it, the type of radiation involved matters, not just the absorbed dose, which is the raw amount of energy delivered. So the formula which deals with type of radiation is the equivalent dose. So you can think of all these measures of doses, they're increasing sophistication. So the equivalent dose, measured in sieverts, H, is the absorbed dose, this is the dose we already understand, times by the weighting factor. Now the weighting factor is like a badass factor, it's a measure of biological harm. That weighting factor depends on the type of radiation, because different radiations have different ionization, ionizing to different degrees because they've got different amounts of charge, and so they penetrate to different depths, and so they have different danger factors, weighting factors on the data sheet. So H equals D times W subscript R. If you want the triangle, there's the triangle. Okay, so this is the next level of sophistication in terms of the dose formula. So we've gone from absorbed dose to equivalent dose, and the most sophisticated measure of the dose is saying, hang on, something else matters, and that's the amount of time that you're exposed to this radiation for. So the time length of the exposure matters too. So the final type of dose to be aware of, which is the one we actually use if you get involved in the nuclear industry, is equivalent dose rate. So equivalent dose rate, H dot, is the equivalent dose H divided by time. So H dot equals H over T, and there's the triangle. Equivalent dose rate, because background levels of radiation are so relatively small, the equivalent dose rate is quite often given in sieverts per hour, or sieverts per day, or sieverts per minute. Now if they want the answer in that, then leave the time in days or hours or minutes, whatever. Okay, so just be aware of that. Sometimes it's easier not to convert the time to seconds as you normally would if the answer they want isn't involving seconds. Just leave the time units in the same units that equivalent dose rate is going to be in. How long is a radioactive thing radioactive for? Well, that varies, but every radioactive thing gets less radioactive over time, because every radioactive metal is made of atoms, and radioactive atoms, then decay is a one-time event, which is a bit like a one-time code. So once it's spat out a bit of radiation, it's not going to do it again, it's no longer radioactive. So the radioactivity of something always goes down over time. Now some things are radioactive for billions and billions and billions and billions of years. So if you're saying how long is it going to be radioactive, well, you're talking billions and billions and billions and billions of years, so that's not really a practical measure of time. So we have like a half-life time. So the half-life time is the time it takes for the radioactivity to fall to half of its original value. So if you're given a graph, look at the original value, half it, go across and down, and that's the half-life time. How do you measure the half-life time of something which is radioactive? Well, you're going to need to plot a graph, aren't you, of activity going up the way and time going along the way. So you have your lump of something radioactive, you have the Geiger-Müller tube which picks up the radiation from it, but it's also picking up some background radiation. So what you have to do is measure the background radiation first before you've got any of the radioactive material out. So you're measuring the background radiation first, which in this case is red. Then you get your radioactive thing out and measure the activity of the radioactive thing every however many seconds. It might be every 30 seconds or every minute or whatever. So you're getting the activity and time readings, which you can plot on the graph, but before you plot it on the graph, you subtract the background reading. Okay? Once you have got the half-life time of a radioactive material, why the hell would you bother doing that anyway? Because it gives you predictive power. So if you know the half-life time of radioactive material, you can work out what the activity is going to be at a certain amount of time in the future. So for example, if the starting activity of something, a lump of radioactive metal, is 2000 kilobecquerels and the half-life time is 4 hours, you can find the activity after 4 hours, sorry, after 12 hours by saying 12 hours divided by 4 hours, which is the half-life, is 3 half-lives. So in 12 hours that's going to be 3 half-lives away, so half the